Welcome to the Chapter 7 podcast. This is the first podcast I've ever done, and we'll see how this one goes. This chapter is on Newton's third law of motion. It's often called action and reaction, and we'll see why in a minute. Now here's the big idea. For every force, there is an equal and opposite force. A lot of times we think that if we apply a force to something, we're pushing on that object, but in reality, the object also is pushing back on us, and we're going to see that pretty clearly by the end of this chapter. Now here's the basic idea. Force is always part of a mutual action that involves another force. That means forces always come in pairs. Here's a little review. A force is a push or a pull when you push on, but here's the point. When you push on the wall is also pushing back on you. There's a mutual action, meaning there is an interaction between you and another thing. It doesn't matter what force you're talking about, there's always going to be an interaction between two things. One pushing on one, the other pushing on the other, one pulling on one, the other pulling on the other. Let's look at a hammer. Hammer hits the nail, and of course it drives the nail into the board. But when you think about it, the hammer stops, so there's got to be a backwards force on the hammer to halt it, to keep it from continuing to going. That force from the nail is changing the motion of the hammer, and this is where Newton figured out that if the hammer exerts a force on the nail, then the nail's got to exert a force back on the hammer. So here we're always talking about pairs of forces. In this case, one of the forces is acting on the nail, and the other force is acting back up on the hammer. Now this is one of my favorite demonstrations. You can try this the next time you come to a glass door. Push on the glass door, not on the handle, but push on the glass of the door to move the door. You're obviously putting a force on the door because you're moving the door. But if you can look at your hand through the window, you'll see that your hand is deformed. There's obviously a force making a change on your hand. So while you're applying a force on the glass is applying a force back onto you. So let's think about this. Does a dynamite contain force? The answer to that is no. It's not something you can have. It's an interaction. It isn't something you possess. You can possess the energy to make a force. You know, when you eat something or you put gas in a car, you're giving it energy so that it can later convert that into a force, into, say, I don't know, running, if once you eat something, or for a car to move by turning its wheels. In this case, the dynamite can cause a force, but it has to possess energy to create that force. So why do forces always occur in pairs? Because it's always part of a mutual action that involves another force. Okay, here's section 2. This is it. This is Newton's third law. It states that whenever one object exerts a force on the second object exerts an equal and opposite force on the first object. You might know this as, for every action, there is an equal and opposite reaction. Let's look at some of these. We're going to look at action and reaction forces. So we're looking at two forces in this interaction. One's going to be called the action force. Let's say, for this example with the runner, the action force is the runner pushing on the ground. In response to that, the ground will cause a reaction force that pushes back up on the runner. So we're going to talk in terms of action and reaction forces. Now, here's the important point. You gotta have both forces. They can't exist on their own. You can't have one force. It's always got to be in a pair. And another rule about this is that they have to be equal in strength and opposite in direction. If you push down on the floor with 10 newtons of force, the floor is going to push back on you with 10 newtons of force. And if you push down, it's going to push up. And another point is they both have to occur at absolutely the same time. They're simultaneously. Here's that law. Here's another way of stating it. To every action, there is an equal and opposite reaction. I'm sure you've heard of that. And here's another point about it, is it doesn't really matter what we call an action force and what we call a reaction force. Sometimes it's hard to tell which one's the action force and which one's the reaction force. For instance, let's look at the example I just circled here with the, looks like a space shuttle and the Earth. The Earth is pulling down on the space shuttle. That's the red arrow right here. But the space shuttle is also pulling back up on the Earth with the same amount of force. So let's say the space shuttle weighed, I don't know, 2,000 newtons or whatever. I'm sure that's small. The Earth is pulling it down by 2,000 newtons. That would be its weight. But it's also pulling back up on the Earth with 2,000 newtons. We can see that with other examples as well. The car here is pushing down on the ground, and it's pushing a force back onto the pavement. The wheel is. The pavement is also pushing the wheel forward, and that's causing the car to move. The car itself isn't causing itself to move. It's the force of the ground back onto the car that's causing it to move. And there's some other things too. You can see you push on a refrigerator. The refrigerator is going to push back on you. Here's an air cart. You push on the cart. The cart's going to push back onto your hand. Now, here we go. Here we're talking about it occurring in pairs. You push against the floor is going to push simultaneously back against you. The tire of the cars interact with the road to produce the car's motion. This is what I was just talking about before. The tire is going to push back on you. Here's one you may not have thought. When you swim, you're pushing on the water, and the water is actually what's pushing you forwards. Your action force is pushing on the water when you stroke or kick, and the water then is pushing back on you, and that's actually what's making you travel through the water. Now, all these reactions depend on friction, and if you don't have a lot of friction, you're going to have a problem exerting a force. As you can see that gentleman who's about to slip and fall on the ground. If you're slipping and sliding, you can't get good traction. I think I definitely know on the athletic field I've had times where it's been a muddy field and it's hard to run in a muddy field because you just can't get the friction between your cleat and the ground. So without the action force, there can't be any reaction. If you can't get any traction, you're not going to be able to go forward. Now this is kind of a clever picture. When the girl jumps to the shore, the boat's going to move backwards because as she pushes on the boat, there's nothing keeping the boat into place. So she pushes one way to apply a force to the boat to push her onto the dock, but she's pushing on that boat, causing the boat to go backwards. You can see that by standing on a wheeled chair and trying to push off the wheeled chair. You're going to push back on the wheeled chair. It's going to go one way. You're going to go flying the other way. And here's another one. The dog wags the tail, and the tail wags the dog. Have you ever seen a dog shake from wagging? That's what you're seeing. So what happens when an object exerts a force on another object? Newton's third law states that the second object exerts an equal and opposite, and I have to add simultaneous force on the first object. Now, we can look at action-reaction forces. We can call them A and B. If the action is on A, then the reaction is going to be on B, and this seems really, really simple, and it actually is pretty simple. Alright, let's try to figure out how to figure out action-reaction forces. Basically, what you're doing is you identify an interaction between two objects, one applying a force on the other and the other applying a reaction force. We'll call one object A and the other object B. So we can state the forces in the following manner. Object A exerts a force on object B. That's our action. Our reaction, object B exerts a force on object A. I always like to say A acts on B, B acts on A. Sometimes it's not so easy to figure this out. What would you say the action-reaction forces are in the case of a falling boulder? Now, don't forget the Earth. The action might be the Earth exerting force on the boulder, pulling the boulder down, but the boulder also is simultaneously pulling back up a force on the Earth. Here's some other ones to ponder. First one, action, tire pushes the road. Well, it's easy. Road will push tire. Action, Earth pulls ball. Well, ball pulls on Earth. And rocket pushes gas. Gas pushes rocket. Now, we'll talk a little bit more about the rocket and the gas because it's not what it appears to be. So if the Earth pulls on the Moon, does the Moon also pull on the Earth? And if it does, which one pull is stronger? Well, that's kind of a silly question because they pull on each other with equal and opposite force. Just like I said before, the Earth can pull on the space shuttle, or it can even pull on you, which is your weight. The Earth pulls on you with 600 newtons. You're going to pull back on the Earth with 600 newtons. And the analogy they make is a lot like saying distance. It doesn't matter whether you're measuring between New York and San Francisco or San Francisco and New York, the distance is going to be the same. So in that case, the Moon is pulling on the Earth as much as the Earth is pulling on the Moon. So how do you identify the action-reaction forces in interaction? You first identify the two objects, A and B, and then you say the action is A acting on B, and then the reaction must be B acting on A.